Hi to everyone. I am Fatih Ersan from Aydın Adnan Menderes University, and I'm working in physics department as an associate professor. And for this session, I will be organize the presentations, and this is the 8th session of this Congress, and in this session we have 5 speakers with 5 novel presentations. The first presentation is from Professor Dr. Saim Emin. He is an invited speaker. Let me give you some information about Professor Emin. Mr. Saim Emin received his Master of Science degree and philosophical degrees in 2007 and 2010 from Saitama University, Japan. In 2010, he joined the National Institute for Material Science to Tsukuba, Japan, as postdoctoral researcher. He was promoted to assistant professor in 2013, and in 2013 at the University of Nova Gorica, Slovenia. And Dr. Emin was a recipient of a prestigious Marie Curie Career Integration Grant. Currently, Dr. Emin is an associate professor at the University of Nova Gorica. He has organized many international congresses, including the Nano-Mat Conference series, and he has published over 35 papers in peer-reviewed international journals. We thanks to Dr. Emin to accept our invitation and share his knowledge with us in this Congress. Let's give the turn to the Professor Emin. And his presentation will be about electrocatalytic hydrogen evolution with transition metal-based compounds. Okay, Professor Emin, you can please start your presentation.
Thank you for the invitation. I especially thanks Professor Yasemin Çiftçi. It's a great honor for me to talk at this conference, which is specialized on hydrogen. It's good to see that also in Turkey there are strong initiatives on hydrogen research, and I hope this takes even wider scales, and one day hopefully it becomes an industry. So I just want to say there are people joining the room, and I see that it asked me to click. Perhaps maybe you can do this right. So
I will do it. Yes.
Okay. Well, in that case, I will start my talk. We explored several systems for hydrogen production, electrocatalytic hydrogen production. And I wrote broadly the title. It was difficult to write a concrete title. So I will explain all of these systems. First of all, about our university. I hope you can hear me well. Is it clear, the sound? Okay, great. The University of Nova Gorica is located at the border town with Italy. It's in Nova Gorica. We are a private university, but we have access to all funding for research and also for education from the country. It was established in 1995, the university. It's a small university, however, it's a research-oriented university. The outline of my talk will cover synthesis of metal selenides, metal phosphides, metal carbides. Then I will give examples on electrocatalytic hydrogen evolution studies, and some summary and future goals I will also present. Why hydrogen? We already heard quite many talks about behind hydrogen, that it's energy carrier, carbon-free, burning of hydrogen, produce energy, and pure water. can be used to produce electricity in fuel cells, and very important here is combat negative electricity prices. Sometimes when the electricity is produced in large quantity, especially from renewables, in that case it comes to the question what to do with this excess electricity. And the best way is to produce fuels, and hydrogen is one good candidate for that purpose. Production of hydrogen can be achieved in many ways. One of the commonly way industrial is cracking, steam reforming, also cracking of hydrocarbons. However, these are fossil fuels, so methane is a fossil fuel. The best choice is to do electrolysis of water using renewable energy sources like wind, solar, or even nuclear. Nuclear is also not, it's, I think it's as a CO2 footprint, it has also quite low footprint. Well, there are many, nowadays there are many companies which are specialized in producing electrolyzers for water electrolysis. And one of the leaders in this area is Hydrogenics. Worldwide, they're installing these hydrogen stations. In this business are also Siemens, Fumatech, Thyssen Group. So there are many companies involved already in hydrogen. And also there are available cars, and the infrastructure is growing. So in the near future, we can see more and more share of hydrogen in comparison to also electric cars, which are also now growing. The way to produce hydrogen, it was reported very early. Electrocatalytic hydrogen production, I saw in Scientific American journal. In 1891, there was a paper on this topic, but first demonstration, it was even further before even this experiment. Steam reforming is we take methane in the presence of water and catalyst at high temperature. It is so it is this molecule is broken, and we get a hydrogen molecule. This is good. It's cheaper than water electrolysis. However, the problem is that it uses fossil fuels. So, and transporting methane is you need infrastructure, pipelines, and so on. You cannot liquefy it. It's difficult to do that. I mean, its cost efficiency is not there. So, electrolysis is the best way to do. And how we do electrolysis? We take power supply, and we need two electrodes. One is anode, the other is cathode. I mean, one is positive, the other is negative electrode. And by applying electricity with sufficient voltage, we can produce hydrogen and oxygen in each electrode separately. Ideal minimum voltage usually is like 1.5 volts. Why is this 1.5 volt, 4/8 more specifically? Because we have losses. Usually in acidic environment, water reduction is defined at 0 volts. This in the scale of reversible hydrogen electrode scale. So, and water oxidation at 1.23 volts. And the difference is 1.23 volt between the reduction and oxidation. However, we have losses, and because of these losses, we need high voltage to apply. The prices of hydrogen at the station can cost like 8 euro per kg, roughly depends on who is selling it. And here is the example of how water is, hydrogen is produced using electrocatalysis. We have a cathode, protons are reduced, two molecular hydrogen, and water molecules are oxidized to oxygen molecule. And on the right side, we have the, if we change the potential and we record the current, we can see at 1.23 volt and a little bit more than that, it starts to increase the current. And the current is a measure of ongoing oxidation reaction. So in the case of hydrogen evolution, it's the reduction this current, which is at negative potentials. Here I'm speaking about positive and negative potential because we use 3-electrode system. So, and it comes below zero if we plot it in the scale, a reversible hydrogen electrode scale. Okay, and not every material has a good that kind of catalytic activity for hydrogen evolution. Some are good, some are bad, and this is measured with this current. And sometimes from this perfect case, which is around 0 volt, we have a shift in negative direction. And this is the overpotential, which we call it. And we basically record that value. And for different materials, it's different. Okay. Our potential for platinum, which is a very good catalyst, is quite low. It's not perfect zero, but let's say 30, 40 millivolts, somewhere there. And nowadays, there are different classes of catalysts developed and studied, so they can evolve hydrogen at, let's say, close to platinum. And these are the metal phosphide, metal selenides, metal sulfides, metal carbides, transition metal carbides. And this makes them quite attractive, this class of material, because platinum is very expensive. And initially, why platinum is good? Because the adsorption of hydrogen on platinum surface and the desorption is very balanced. It's close to zero here. And that means this is one of the good systems for hydrogen evolution. However, by tuning the composition of materials, it's also possible to tune the strength of adsorption and desorption, which hydrogen will experience on the electrode surface, and design catalysts. And eventually replace platinum. So platinum is very expensive. There's platinum group metals, like rare earth metals, they are very expensive. 30, 40, $50,000 per kg they can cost. And iridium is one of the very good materials, and ruthenium to, for example, oxidize water. Platinum, palladium, they are good for water reduction, let's say. And as I said, these metal carbides, transition metal carbides, are very good candidates, especially tungsten carbides, because they are very robust. They are stable. They can operate in acidic, in alkaline environment. Metal carbides are good for hydrogen evolution studies. Metal selenides also are good for hydrogen evolution studies. Some are even bifunctional, like metal phosphides. They can be also used for water oxidation studies. And the approaches which are used for synthesis of carbides are a reduction of tungsten precursors with carbonaceous gases, pyrolysis of metal organic frameworks, reaction of some tungsten salt with let's say molecules like guanidine, hydrochloride, chemical vapor deposition. Same for selenides. Selenides can be produced hydrothermally. Hydrothermal synthesis means we need a precursor for the metal ion and for selenium ions. Selenization of tungsten containing materials like tungsten oxides, electrochemical synthesis, CVD approaches. We use the colloidal synthesis, where we did pyrolysis of tungsten hexacarbonyl at high temperature, like 230 degree. And in this compound, tungsten is in oxidation state 0. So basically, after heating, it loses the CO2, CO, and carbon monoxide, and reduces, it forms nanoparticles here. They are amorphous, difficult to see them, but we initially the solution was transparent, so it developed this black color, and which give a clear sign that particles grew. What we have is we have metallic nanoparticles covered with some molecules, and they are very well dispersed in organic solvents, not in water. And we can spin coat them. Basically, they are very stable. Once it's synthesized, they can be stable for years. So I have samples from 2018. They're still stable in my drawer, dissolved in a solvent chloroform. And after spin coating, then we can decide for what purpose we can use them. We can use them for production of carbides or selenites. If we heat in Earth atmosphere at very high temperature, and if they are coated on carbon substrate, we can produce metal carbides. If, for example, we put in the tube furnace selenium precursor, let's say selenium shots, which will evaporate at high temperature, and then they can grow. We can grow tungsten diselenides or molybdenum diselenides, depending on the type of precursor we use. And what we did is we coated on the graphite these electrodes. Some of the studies were also done with FTO, fluorine ductine oxide, but the graphite is cheap, so we took this graphite, cut it in pieces, and put it in the tube furnace and heat at high temperatures. And we were able to do this different phases of tungsten, like here you can see the reference, which is W2 or C. This is one phase of tungsten. Another is a WC. These peaks, these are the reference, and you can see here the peaks are for at high temperature we can grow the phase with high oxidation state, which is VC. All is fine. This is the phase diagram, two-phase diagram for two-component system, tungsten carbon, and we can see which kind of phases can form at what temperature. So we were able to synthesize it at low temperature because nanoparticles are more reactive. And here you can see an SEM image of this carbides. First, initially, after heat treatment at high temperature, like 900 degree, these particles crystallize to metallic tungsten. And when we exceed 900 degree, then they form the carbide. And this SEM image is recorded with backscattered electron detector. So there it's different from secondary electron detector. With secondary electron detector, you cannot see this kind of contrast. With backscattered electron detector, you can see, and the white spots are the tungsten particles. We did some TM studies. Then we found that these are carbides are formed. Then we tested the electrostatic hydrogen evolution. On the left side is this current potential plot. As I said, higher current. The current is a result of hydrogen evolution. And if the current is close to zero, increasing steep, so it's better. As you can see, platinum is much better. Platinum carbide is much better than the other films. However, our study was a conceptual study. So how we can produce from metallic this tungsten, from metallic tungsten to produce carbides, and after that use these carbides in hydrogen generation. And on the left right side is a plot of hydrogen evolution at fixed potential. As you can see, the current is quite stable. Initially, it increases. After that, again, it stabilizes. Means the generation of hydrogen is stable. Here you can see a movie. Let me show you. You can see on the two electrodes, we have evolution of gases. On one side is hydrogen, on the other side is oxygen. The blue color is because of dye. We also use this in dye wastewater treatment, the oxidation, this part where oxidation reaction happens. Okay, next slide. Well, I will explain the next is about tungsten diselenides and molybdenum diselenides. The same particles which we synthesized early, we coat them on graphite substrates and did selenization. Selenization was done in a tube furnace where we also put selenium shots in a separate cup. And after heat treatment, selenium vaporizes. So it melts and the vapors then goes to the tungsten film, and it in this way it grew these selenium films, tungsten diselenide films, and also molybdenum we used. Here is images of molybdenum nanoparticles, which we also used to grow molybdenum diselenides. As you can see, they are very small. They are amorphous. We don't have so many spots. As you can see, the electron diffraction is quite blurring. There are a few spots, but compared to the number of particles, this is basically very little. So majority of these particles are amorphous. And we recorded the diffraction patterns of these films. And with dotted line here are given the peaks for this tungsten diselenide and also molybdenum diselenide we recorded. And we can see that they are growing. And by increasing the temperature at 800 degrees, we get a better crystallinity. Here are SEM images of the films, which we grew. Okay. Here is an elemental mapping of a small piece of material using TEM. This with energy dispersive spectrometer, we recorded the tungsten and selenium, so we know that they are made of this material. XPS analysis also shows that a little on the surface we have a small layer of oxygen. Most probably it oxidized partially, but it's very little, just on the surface. And then we tested for hydrogen evolution. What we found is the overpotentials by increasing the temperature. So we didn't see so big difference. One of the film was not so fine, around 290 millivolts at 10 milliamp per square centimeter was the overpotential. The film which was not good was basically the one with the cracks. So the cracks can be avoided. We also later find the conditions how to create films without cracks. Okay, at decreasing the ramp heating and cooling ramp. And using the same method, we grew molybdenum diselenide films. And as you can see here, we have different films annealed at different temperature, heated at different temperature, 750, 800, 850. However, we also optimized we calculated also the area, measured the area of the films, and then normalized it. After normalization, we saw that basically 800 and 850 give the same activity. And on the very right side is the again stability this plot. Initially the current drops, but later with the time it stabilizes. And after stopping and running again the experiment, it's repeatable. So there is some kind of charging on the graphite surface. However, the fact that it's stable, this current, it shows after, let's say, 60 minutes in the first experiment, and in the second, after 240 minutes, it showed that films is stable. Films are stable. We collected the hydrogen, and we saw that it is repeatable. It doesn't lose activity. Hydrogen was detected using mass spectrometry, and at this point, injection point at 30 seconds, we injected with syringe the gas which we collected, and we have sudden increase in the current. And after we took out the syringe, and when the mass spectrometer head is exposed to air, again it drops. So we can prove in this way that we generate hydrogen. Another, I have very little time, but I will try to squeeze and to go faster, are the metal phosphide, transitional metal phosphides. They are also very attractive. In the literature, they were reported both as hydrogen for hydrogen evolution and oxygen evolution studies. There were many studies about synthesis of these materials, how to synthesize them. And this was done in the context that they were used in also biological studies because of their fluorescence, some of them, indium phosphides especially, using single precursors, using CVD approaches at different temperatures. Okay. And
Professor,
yeah.
Professor, sorry, you have 5 more minutes.
Okay, very soon. In 2-3 minutes, 3 minutes, I will try to finish.
Okay, thank you.
The metal phosphide we used was iron phosphide. Iron phosphide can appear in 6 phases. One is Fe3P, Fe2P, and FeP. FeP2 also there is. When we increase the content of sulfurs, they become semiconductors. These two are metallic. We also calculate the density of states. The calculation was done by Dr. Masabhar from KAUST. It is known the density of states for this material, but we use it for some other purpose, which I will not show here because it's about different study. However, I can say that they are metallic, these materials. Well, the synthesis of metal phosphides was done using iron pentacarbonyl precursor in the presence of a molecule called triphenyl phosphine. So this molecule is, as a phosphorus source, is quite cheap compared to the other precursors which are used in the literature. And at 300 and 350, we can grow different phases. At 300, we can grow Fe2P, and at 350, we can grow FeP. So by increasing the amount of phosphorus, we can grow a phase which is rich in phosphorus. And here is the diffraction pattern of these two phases. And we have them in pure form, both materials. The references are given also here. And they correspond to perfectly to the one in the database. And then we took these materials and tested again in electrocatalytic studies. This time we were able to achieve all potential for hydrogen evolution at 10 milliamp per square centimeter, about 110 millivolts. This is in acidic environment at pH close to 0. And this was achieved with a film heated at 500 degrees. So after synthesis, we need to heat the films because we need to remove these organics which are on the surface of the particles. They block the catalytic activity. So the heating was done at 500 degrees Celsius under reductive atmosphere. For a purpose, we use this reductive atmosphere. We can also cause some kind of phase transition inside the material by heating in hydrogen atmosphere. And so we were able to produce film very stable, that kind of films. The current is very stable. Here we tested these films at 160 millivolt applied voltage and record the current. And for the one of the sample, you can see very stable. The other, a little drop activity, which means metal phosphides are also very good for hydrogen evolution studies. In conclusion, I would like to say that we used colloidal approaches to synthesize molybdenum, tungsten, and iron phosphide. Some are nanoparticles, some are microspheres. I didn't show all the data using wet chemistry approaches. Spin coating of particles were made on FTO, fluorine doped tin oxide, or graphite electrodes. Heat treatment of tungsten carbide graphite films allowed us to produce samples containing tungsten carbides with different phases. And we found that one of the tungsten carbides mixed phase gives the lowest over potential, around 310 millivolt for HER, for hydrogen evolution. We developed a new approach for the preparation of molybdenum selenide and tungsten selenide films. And also we, for the first time, we explored the phase transition in iron phosphides on the reductive atmosphere and applied it in HER studies. And I would say that colloidal route has been found simple way for preparation of electrocatalysis thin films for hydrogen evolution studies. Financial support was provided by the Slovenian Research Agency under the bilateral project for scientific cooperation with Israel. Special thanks to my students Taka Choki, Manel Machreki, to my collaborator Plamen Stefanov from Bulgarian Academy of Sciences, Abdullah Yildiz from Yildirim Bayezid University, Boranil Domkova, and others whose name appear in the papers. Here is also the website of this project, which completed this year, at the end of last year. And we used, the studies was done with the purpose of wastewater cleaning for growing these wine plants and for wastewater treatment. With this, I would like to thank you for your attention.
Okay. Thank you, Professor Emin, for this good presentation. Is there any questions from the participants? By the way, I hope we can also meet, and we want to host you in Turkey when this pandemic is finished. I hope we can meet and we can host you.
Thank you very much. I would be also very happy to visit you. I was looking forward to visit you this year in person, but unfortunately, still it's a little bit closed the borders, and so hopefully in the near future I visit you, and you are also most welcome to our university.
I hope. Thank you for the presentation, Professor.
Thank you.
Okay, our next invited speakers is Professor Lorenzo Malavasi. Welcome, Professor Malavasi. Let me give you to the participants some information about you. Professor Lorenzo Malavasi received his degree in chemistry in 1999 and a PhD in chemical science in 2003. From 2003 to 2007, he was a postdoc student at Department of Physical Chemistry of University of Pavia. Am I right?
Okay. Pavia, right.
Okay. From 2008 to 2014, he was an assistant professor in same department. From 2015, he is an associate professor at the Department of Chemistry, Division of Physical Chemistry of the University of Pavia. And since 2008, he is lecturer in materials chemistry, laboratory of materials chemistry, chemistry and nanomaterials chemistry, and he is member of the board of the PhD in Chemical Science of the Pavia University since 2013. He is a member of the Academic Senate since 2018 and Vice Director at the Department of Chemistry of the University of Pavia. Lorenzo Malavasi is working in several areas of solid-state chemistry with particular interest in the investigation of structural properties, correlation in different kinds of functional materials, such as materials for solid oxide fuel cells, photovoltaics, photocatalytic water splitting, and high-temperature superconductors. Lorenzo Malavasi is author of more than 118 publications on international journals. Okay, thanks to Professor Malavasi to accept our invitation and share his knowledge with us in this Congress. Professor, it's your turn.
Thank you so much. Thank you so much for this kind of introduction and for this invitation. Can you see the presentation on the screen?
Yes.
Okay. Thank you so much. So I'm very honored to be here. I would like to thank all the organizers and Yasmin in particular. We have a collaboration ongoing, so I'm happy to deliver this talk today. As you can see from the title is Metal Hyperoxides Photocatalysis, a materials chemistry tour. So in this presentation, I would like to point one of the most recent and challenging and exciting application of metal hyperoxides. I think that most of the people in the audience knows about the perovskite fever that emerged since 2009 when well, I would say not really a novel class, because this kind of hybrid perovskites were already known since 70s and even before, but no one thought they could be used as active layer in solar cells. Anyway, in 2009, this perovskite, methylammonium lead iodide 3, you see the classical perovskite structure, but here there is an halide as an ion. Many of us may be aware of oxide perovskite. Anyway, this perovskite is called an hybrid organic-inorganic, because on the A side of the perovskite, you have an organic cation, methylammonium, and then we have lead. This is a semiconductor. The band gap is around 1.55 electron volt. And the crystal structure is a normal perovskite, where, however, the organic cation is at the center of the cubic tetragonal unit cell and is highly mobile. The main issue is that the fascinating aspect of these materials is that they are very tunable materials. For example, if you just change the halide from iodide to bromide and to chloride, you can modulate the band gap of these materials. Anyway, so in 2009, in this seminal paper, the authors prepared a Grätzel cell, solar cells, by using this semiconductor as active layer. They got just few percent of efficiency, but in this cartoon you see here, in few years from 2010 up to now, the efficiency, certified efficiency of solar cells based on metal hyperoxides impressive, exponentially grow, and now we are more than 25%. So you can see that in less than 10 years, the efficiency of these cells, of perovskite solar cells, grow in an impressive way. However, if you look at what is called the golden triangle of solar cell performance, these new solar cell based on metal hyperoxides have a very good cost with respect to traditional silicon solar cell. Also, in terms of efficiency, they are good. Of course, the real problem of these solar cells containing metal hyperoxides is the efficiency, the lifetime, because they are very moisture sensitive, and also they tend to degrade under continuous illumination. Anyway, they are extremely interesting, and we may expect in the next 5 years to see on the market these perovskite solar cells, also because they can be printed, so you can prepare flexible solar cells, which cannot be done with silicon. However, our approach, we started in 2015 to investigate this material for optoelectronic and photovoltaics application, but we thought a couple of years ago that, well, in the end, metal hyperoxides are semiconductor with superior optical properties, okay? So why not try to apply them in photocatalysis? Essentially, a good photocatalytic material should have a broad and strong light absorption, and perovskites have this. Here you see how can you easily tune the visible light absorption by changing, for example, composition. These are emission spectra. Of course, you also need for a good photocatalyst a very efficient charge separation to promote the redox reaction, and this is the case of metal hyperoxides. They intrinsically have very good charge carrier separation efficiency. Of course, redoxability for target reaction. Here you see a plot where you have some relevant, the redox potential of relevant photocatalytic reactions such as CO2 reduction, hydrogen photogeneration, even oxygen photogeneration. And here you see a series of traditional semiconductor used photocatalysts currently used, such as titanium dioxide, graphite carbon nitride. And here you see the band level alignment of some metal hyperoxides. For example, you see here formamidinium lead iodide 3, Fa is formamidinium. Here you see cesium lead 3 iodide, and so on. So basically, they have the potential to run most of the relevant photocatalytic reaction. Of course, long operation stability is still a question also for their application in photocatalysis. Okay, so what we have done in my group in the last years is to apply a rational materials chemistry design to try to devise novel materials for photocatalytic application based on metal hyperoxides. So I will make a tour today highlighting some of our results, okay, just a part of them, okay? So basically we want to use the metal hyperoxides to run photocatalytic reaction. Of course, which is a state of the art? The state of the art is that they have already been extensively investigated, for example, for hydrogen photoproduction. Here you see, for example, one on our recent review on the use of metal hyperoxides for hydrogen photogeneration. I will not go into details, but many different phases have been used. They have been applied also for CO2 photo reduction. Okay, so for example, in particular, in this case, quantum dots of this composition have been, quantum dots of this size, more or less 10 nanometers or even less, have been used in composites with graphene oxides to reduce CO2 to carbon monoxide and methane with, you see, a very impressive selectivity, okay, against the proton reduction. They have also been applied for photo reaction, organic transformation reaction. We are also working on that. So here there is a short list of the organic reaction where metal hyperoxides have been used as photocatalysts. You see very interesting reactions, okay? So, which is the aim in this case? We want to extend the application of metal hyperoxides in photocatalysis. This is a field that can be defined to be still at infancy, but of course, with a great promise, and which are the aims: improve long-term catalytic cycling, operational stability, improve the activity for hydrogen photogeneration, CO2 photoreduction, expanding the scope of organic transformation and develop new key chemical reaction, and in general, enhancing the redoxability of metal hyperoxides. Again, here, the main issue is to provide a rational materials design. Let's start with the materials in bulk form, then move to thin films, create photocathodes, create device. Okay, so this is the route we usually apply in our research in this case. Okay, so let's start with some example. One of the first example of 2-3 years ago was the investigation of this system. Well, I have to make a point here. in my group, we essentially work in lead-free metal perovskites. Most of the people are interested in lead-based materials because, of course, they are the most efficient one, but it's hard to believe, in particular in Europe, that we will ever see a solar cell containing lead. Okay, so we essentially work on lead-free materials. So you will see a lot of tin, bismuth, and other stuff like this, but not lead in our works. Okay, so let's start with this system. This is a very simple system: methylammonium, tin, tribromide. We try to replace methylammonium with dimethylammonium, slightly longer and more hydrophobic cation. Okay, we expected some improved water stability. Also, another point, in general, all these metal perovskites are highly water unstable. If you take these metal perovskites, you put in water, they destroy, because they are highly ionic crystals. So of course, this is a problem if you want to run photocatalytic reaction, this water instability. Anyway, we prepared, for example, this solid solution. You see that when you move from methylammonium tin tribromide to dimethylammonium tin tribromide, the color of the powder changes. You have the band gap moves from about 2 eV to close to 3, okay? Okay, there is a miscibility gap. You cannot repair the full solid solution, but these are details. Here you see some absorption spectra in the tau plot of the series by changing the relative amount of dimethylammonium. So starting from the red, it's pure methylammonium tin tribromide, to dimethylammonium. Anyway, okay, these are the basic. You can have a very good band gap tuning just by replacing the organic cation. The point is that we then investigating the aging effect of these materials, in particular of the methylammonium tin tribromide. And the aging was first done by exposing these perovskites to air. Here you have tin 2 plus, okay? Tin 2 plus is easily oxidized to tin 4 plus, and you destroy the perovskite. Anyway, after 6 days of air exposure, and trust me, in Pavia, where I live, we have a very huge humidity. We are around 40%. In this season, we are 40% of relative humidity and even more. So in moist air, and the perovskite, the diffraction patterns were fine. Optical absorption was still fine. So we could observe a good air stability, which was a quite impressive result for a tin-based perovskites, and in general for a perovskites, because also many of these, also the lead containing perovskites, if you're exposed to air, they destroy, okay? But then we went even farther. We put the perovskite in water, and impressively, what we could see is that in this perovskite does not dissolve in water. It remained dispersed in water, okay? As a matter of fact, when we recovered the perovskite from water, the diffraction pattern was perfectly as it was after as prepared, and also the optical properties were still conserved. So this was a quite impressive result. To be honest, in those months when we discovered this behavior, another group observed the same behavior on the iodide analog. And so also XPS, look, the tin 3D position of the peaks of the as prepared material and after water didn't change. Tin remained tin 2 plus. So in some way, we thought that this dimethylammonium cation could protect the tin from oxidation, and in general perovskites from water sensitivity. So the idea was how we can use this. So our idea was initially to try to develop hydrophobic metal perovskites. The first test we did was to try to use it as a photocatalyst. So we use this perovskite as bulk material with a sacrificial agent under solar simulation, and we could observe 6 micromoles gram-hour of hydrogen, which of course is a tiny amount, but this was the first observation of hydrogen photogeneration by a tin-based metal perovskites in water. Of course, then what we thought to take advantage of these superior optical properties of metal perovskites and this impressive stability of these perovskites, and we thought to create heterojunction with other active photocatalysts, and in particular we selected graphite carbon nitride. We run a lot of work on this material. So we create composites, heterostructure, by combining graphite carbon nitride, which is a visible light photocatalyst absorbing it's a yellow material with a band gap around 2.7 eV. And we create composites, okay? We skip the detail on the synthesis, okay? And the main result was that we could improve the hydrogen evolution rate by improving the amount of metal perovskites loading with respect to the graphite carbon nitride. And we could achieve something like close to 2000 micromoles per gram hours of hydrogen photo generation by this kind of composites, okay? So this was a quite interesting and fascinating results, okay? Was the first one we achieved with our idea of using metal perovskites. We also investigated the mechanism. The basic idea is that the perovskites, there is a transfer of a charge carrier between the perovskites and the graphite carbon nitride. So we effectively create an heterojunction because, of course, here we achieve something like this as value, but the graphite carbon nitride alone is, you see, very low amount of hydrogen, and also the perovskite is quite low alone. So we have a synergy between the two. So we effectively created an heterojunction that improves significantly the hydrogen photogeneration reaction. So under the optimal condition, we could really achieve an hydrogen evolution rate greater than 1,700 micromoles of hydrogen. Okay, so thanks to this good band alignment. This was a quite nice result. Of course, these, to be honest, these are not, in any case, the most stable perovskites you would like to work with, because you have then the tendency of T reduction after the reaction. So it's anyway a complex system. It was a demonstration that you can play with them, but of course we are not moving toward more stable systems. In this case, the idea is to reduce the dimensionality of the perovskites and play with the two-dimensional perovskites, because two-dimensional perovskite, okay, here you see the tri-dimensional perovskite as I showed you before, like dimethylammonium, tin, and tribromide. In the two-dimensional perovskites, you see you have a layer of inorganic framework of octahedra, for example, tin, bromine 6, and this layer of octahedra is separated by organic spacer, which can be even very big. These perovskites are more stable towards water, for example, because here you can put very huge organic cations, and again, you can very easily tune their properties, their optical properties by chemical substitution. So one of the first systems we investigated is this one. PEA means phenylethylammonium. Here you see the crystal structure. So it's phenylethylammonium 2, tin, tribromide. So you see the structure, you have a layer of octahedra. Okay, this is a rootless and popper perovskites. You have one single layer of tin bromide 6 octahedra separated by two phenylammonium cations. So you see, you still keep the properties of the inorganic framework, tin tribromide, which dominate the electronic properties in terms of band gap and absorption, but then you have these organic spaces that improve for example, water stability. This was a new perovskite, never prepared in the literature. We prepared it by wet chemistry, and immediately we tested the water stability. Perfect water stability, diffraction pattern after and before dispersion in water. Again, also this perovskite does not dissolve, but it is dispersed in water. You can see the perovskite, the particles of the perovskites. Optical properties are good as prepared and after water material, and also the XPS 3D of tin is fine, and it is again tin 2+. Okay, so again we prepare composite, so heterostructure, by combining this perovskite with graphite carbonitride, again because the band gap are similar, so we may expect a good band alignment, so a positive charge transfer between the two. And as a matter of fact, this is another recent paper. If you look at the hydrogen evolution rate of the pure perovskites, about 4 micromoles of hydrogen, of the pure graphite carbonitride under the same condition, 81. The composite with 5% of perovskite goes up to 1,600. So another very good synergy between the two materials in creating the heterostructure. And also, we also tested these composites against organic dye degradation. Here you see, for example, the composite and the pure graphite carbonitride. So composite, the heterostructure works better. And again, we also thought about the mechanism. Again, there is an effective transfer of the photoinduced electrons from the perovskites to graphite carbonitride, okay, due to the fact that conduction band maximum is lying at a less negative potential. Okay, so this is another example we are working on, and we are exploring other phases and just picking up some representative examples. We are moving further.
Sorry, Professor Malavasi, you have 5 minutes.
Yeah, okay. Yeah, I'm going to the end. So, for example, this is a very recent system we are working on. You see, we are changing. We are going to 0D perovskite with bismuth. Again, we created composites with graphite carbonitride. You see, pure graphite carbonitride is here. Here we need just 2.5% of the perovskite, and we can go from 50, 60 micromoles more than 1,000, okay? So I will not go in detail. Also in this case, we have a good electron transfer between the perovskites and the graphite carbonitride. And we also, thanks to our colleague in Perugia, we also could interpret the behavior of the hydrogen evolution reaction as a function of the loading of the perovskites that has a maximum and then decreases, okay? I will not go too much into the details, okay? Of course, starting from powders, we move to thin films. We prepare these thin films by magnetosputtering, so vapor phase deposition. You see, you move the band gap from yellow to red. If you move from bromide to iodide, films are very good films. Okay, diffraction patterns. This is the morphology. We also prepare some nanocrystal, and we already tested them for organic dye degradation with methyl blue. And you see the pure perovskites in the photo degradation are quite effective. They are effective as graphite carbon, pure graphite carbonitride. So now we are moving to photocathode fabrication with pure materials, but more interesting with the heterostructure. Just to give you another very quick example, I will not go into details. We are expanding, of course, our interesting towards organic reaction in collaboration with the colleagues in the organic chemistry department. And so we are, for example, and also with analytical chemistry, we are, for example, using our perovskites for the single oxygen generation processes. So we are running organic reaction by using our perovskite, our composites with metal perovskites to generate in situ single oxygen, for example, for the Diels-Alder reaction and other organic reaction. You can you have some references here, and we are also applying our photocatalyst on biomass substrates. And finally, we are also exploring the use of nanocrystalline metal perovskites. You see the series of cesium lead tribromide. Here we still keep lead. This is the only case where we keep lead because it's nearly impossible to get a highly active nanocrystal based on tin. You see here the fluorescence of these nanocrystals, and we have used them and we are using them several kind of organic reaction, for example, oxidation of cyclic alkanes or oxidation of acyclic alkanes and many other organic reactions. So to conclude this overview of this tour, I hope I provided you the idea, the flavor that metal-like perovskites are very appealing materials for photocatalysis. And if you look at the current literature, you see every day at least 2 or 3 papers where people are starting applying metal-like perovskites in photocatalytic application. They really work very well in CO2, for example, reduction. There is, of course, still a huge space left for materials and property discovery and optimization in the field of organic synthesis, carbon dioxide reduction, and biomass transformation. And then we still have to explore the application of nanostructure and play with nanostructure to improve efficiency. We are moving in this direction. And of course, start thinking to device configuration. So now we are really working on these 2 aspects of the application of metal-like perovskites for photocatalytic application. I would like to thank all of you. This is a snapshot of the senior in my group, some PhD and postdoc students. And again, thank you for your time and attention. Thanks.
Thank you, Professor Malavasi, for this really good presentation. As you said, perovskites are really very important in these days. And also, I am also working with perovskites. We are working at the simulation part. Maybe I can share our studies with you.
Yes, please.
Maybe we can find a chance to discuss about it. What can we do? Maybe we can collaborate.
Yes, that would be lovely. Sure.
Is there any questions from participants? Yes, there is one question. How do you prove the formation of 2D perovskites? Do you use the XRD pattern or PL spectra from Professor Dr. Saim Emin?
For the 2D perovskites, in many cases, since a new sample, we prepare single crystals and we solve the structure. So since in the group we design novel materials, in general, we pass through single crystal synthesis and we solve the crystal structure. So we really get to the real crystal structure of the materials. Yeah. And then, of course, once you have that, and of course, with these 2D perovskites, since you have seen that you have the octahedra, organic spacer, octahedra, usually you immediately see that you have a 2D because in the X-ray powder diffraction, you have huge peaks at very low angles because the d-spacing along the z-axis is maybe 30, 40, 50 angstroms. So you immediately recognize that you have a 2D. But in general, we always prepare single crystal, solve the structure. Yeah. Thanks for the question.
Is there any questions? I think no. Okay. Thank you again.
Thanks again. Thanks again for your time, and it was really a nice occasion to be here today. Okay. Thanks.
Okay. Our third presentation will be from Meltem Kara-İsmailoğlu Elibol. Yes, and subject is new perovskite electrocatalyst for SOX with internal gasification preliminary results. Welcome to Dr. Meltem.
Thank you very much.
And it's your turn, please.
Firstly, I would like to share my screen with you. Okay. Good afternoon, all. My name is Meltem Kara-İsmailoğlu Elibol. It is my great pleasure to talk to you today about new perovskite electrocatalysts for solid oxide fuel cells. Uh, Here you see the outline of my presentation. Firstly, I am going to make a short introduction to the topic. Then I will move on to look at the experimental part, and I will also try to explain our findings about material characterization and also its conductivity results at the room temperature. And finally, I will summarize our findings and I will finish off my presentation. So, renewable energy technologies attract more attention to overcome the dependence on the fossil fuels and to reduce greenhouse gas emissions, which lead to global warming and climate change. And therefore, we need alternative energy sources like hydrogen energy. Hydrogen is an energy carrier and can be used as alternative fuel, especially in solid oxide fuel cell systems. Here is the electrode materials. I mean, in the solid oxide fuel cells, the electrode materials play a significant role for a high performance conversion of chemical energy into the electrical energy. And in this respect, perovskite type materials are gaining an significant importance. Yeah. In our study, we have prepared perovskite materials via modified sol gel method. And we have analyzed the crystal phases of each electrocatalyst samples via X-ray diffractometer. And also we have determined the specific surface area using the bed technique. And also the microstructure of each electrocatalyst samples were determined using a scanning electron microscopy. And after the preparation procedure, the electrical conductivities of the electrocatalyst samples were measured using an LCR meter, and it happened, like I told before, at the room temperature. Like I said before, we have synthesized each catalyst via modified sol gel method, and in this respect, we have used metal salts for preparing the precursor solution. And in this preparation method, it is important using a sol gel agent. Here you see that in the first table as complexing agent, and here strict acid was used as a complexing, sol gel agent, and we wanted to obtain a high surface specific surface area for each catalyst, and therefore ethylene diamine tetraacetic acid or ethylene glycol was used for surfactant, and the pH of the precursor solution was adjusted to 1 or 8 with the help of ammonium bicarbonate or ammonium solutions. Here in the table, you see the comparison of the preparation methods. And also we have labeled each catalyst with LSCF, which means that each electrocatalyst consists of lanthanum, strontium, cobalt, and iron metals. And one of the most important steps is the calcination step in this preparation methods, and therefore we have choose two different calcination temperatures, and the catalyst with the A series were calcinated at the temperature of 800 degrees Celsius, and the catalyst with B series were calcinated at the temperature of 900 degrees Celsius. And here you see the results for the material characterization. As you see in the second table, each electrocatalyst sample consists of multicrystal phases, actually. And samples marked in yellow were calcinated at the temperature of 800 degrees Celsius. And here you can understand the effect of the calcination temperature very clearly, actually, because, for example, if we take the first sample, LSCF-A1, the catalyst A1 was calcinated at the temperature of 800 degrees Celsius, which has this specific surface area almost like 17 square meter per gram. And the second catalyst, which is calcinated at 900 degrees Celsius, has a lower specific surface area, like 13, almost 13 square meter per gram. And it's, I mean here, the all samples which are marked in yellow has the higher specific surface area compared the version at calcinated at 900 degrees Celsius. And this correlation is also relevant for the conductivity results, actually. I mean, the catalysts which were calcinated at 800 degrees Celsius have a higher electrical conductivity compared to the catalysts which were calcinated at 900 degrees Celsius. And here, the sample LSCF-A4 has the highest electrical conductivity. And here it should be noted that for the preparation of these catalysts, the ammonia solution was used for adjusting to pH to 1, and ethylene glycol was used as surfactant. And here you see this figure displays the SEM micrographs of each catalyst at 30,000 magnification. And these micrographs prove also that the catalysts have a porous structure. So, and now I just wanted to summarize the main points of our study. We have prepared electrocatalysts which will be utilized in solid oxide fuel cells by biogas product gas, actually. And their electrical conductivities were measured at room temperature. However, I have to add that these are the preliminary results. And now we are working on the conductivity measurements at higher temperatures, and we are expecting that the electrical conductivity will increase with the increase in the reaction temperature, actually. And considering our catalyst, the samples calcinated at 800 degrees Celsius have higher surface areas and a relatively high conductivity. So we would like to acknowledge the financial support from Eranet Med project. And I would like to also thank you for your kind attention.
Thank you, Dr. Kara İsmailoğlu, for coming and sharing these novel studies with us. Thank you again. And is there any questions from the participants? I think no, there isn't any questions. Thank you again.
Thank you very much. Thank you. Have a nice day.
Have a nice day to you. Okay, our fourth presentation from Utku Burgun. Hi,
Hello.
welcome, Dr. Utku. And the title of the presentation is Effect of Rare Earth Metals on Zeolite Supported Iron Copper Catalyst for Light Olefin Production by Fischer-Tropsch Synthesis. Okay, it's your turns, Dr. Utku. Please share your presentation.
Okay, first of all, my voice and screen is clear.
Yes, all of
Yes.
them.
Thank you. Hello, I'm Utku Burgun. I'm a PhD student in the Department of Chemical Engineering at Istanbul Technical University. Today, I will present our latest study, which is entitled of Effect of Rare Earth Metals on Zeolite-Supported Iron Copper Catalyst for Light Olefin Production by Fischer-Tropsch Synthesis. Our aim in this study is to investigate the catalyst for the production of high value added products such as light olefins by using carbon monoxide and hydrogen. First of all, I would like to start with why we want to produce light olefins. The light olefins, ethylene, propylene, and butylene, have a very significant place in the petrochemical industry, and these materials are seen as the key components of chemical industry. Many products can be produced from these molecules, and these products have a wide range of use in modern life. The conventional method of the light olefins production is based on petroleum, and it is obtained by the steam cracking of petroleum product naphtha. But due to the limited sources and the depletion of petroleum reserves in the world, or the countries that do not have petroleum reserves, including our country, for that reason, alternative routes have been developed for the production of light olefins. And one of the routes is the Fischer-Tropsch synthesis. In this synthesis, the synthesis gas or syngas is used as the reactant gases, which are the carbon monoxide and the hydrogen. And this synthesis gas is obtained from by the gasification of coal or biomass, or it is obtained from the natural gas. Here, the reactant gases react under the suitable conditions over the catalyst to produce light olefins directly. If we talk about the mechanism of FT synthesis, while the reactant gases in appropriate composition react over the catalyst to produce alkane, alkene, and alcohols, and at the same time, water gas shift reaction and boudoir reaction occur here. Here, the carbon monoxide molecule first dissociates on the active metal of the catalyst, and the first CH intermediate occurs with the addition of hydrogen. And the continuation of the addition of the reactant gases, the chain growth occurs, and the products start to be produced. How should catalysts be? The mechanical and thermal properties should be high, and the chemical physical properties such as surface area, porosity, and composition should be arranged well to provide the activity, selectivity, and stability. Looking at the periodic table, the transition metals, which are the iron, cobalt, nickel, ruthenium, and rhodium, show high FT activity. But the light olefin production of the iron and cobalt is much higher than that, the other metals. When we compare the iron and cobalt, since iron has high light olefin selectivity, low methane selectivity, and due to its lower cost, it is commonly used active metal in the light olefin production. What might be in a catalyst content? Catalysts can have support materials and promoters to prevent the catalyst from sintering and to increase the active metal dispersion. Support materials such as metal oxides, zeolites, or carbon-based materials can be used, and the promoters are the used as here at the same time, and these are the metals which are added to catalysts in low amount to increase the activity and selectivity. In experimental study, we have selected iron as the active metal, and it was added at 28% to catalyst, and the copper was selected as the first promoter, and it was ranged to from 0.5 to 1 weight percent. And to examine the effect of rare earth metals to that system, I mean iron and copper, lanthanum, cerium, neodymium, holmium, and erbium metals were added to catalyst at 0.5 weight%. At first, all metal precursors were dissolved deionized water, and that solution was then co-impregnated to our zeolite supports, which are the ultra-stable Y with a high silica-alumina ratio and mordanite support with a low silica-alumina ratio. And after the drying and calcination processes, the total of 24 catalysts, which comprised 22 promoted catalysts and 4 base catalysts, were obtained. And at first, the performance scanning test of that 24 catalysts were performed by using a high-throughput catalyst performance test system. In the test system, there is a heated reactor block in its size and top, and there are 4 reactor plates, each having 20 microreactors with a diameter of 4 millimeter. So the total capacity of that system is 80 catalysts. And due to its micro design, it just requires so small amount of catalyst, about 10 to 20 milligram. The test system, which has micro gas chromatograph and mass spectrometer, provides performing multiple and rapid scanning tests at atmospheric pressure. And in the high-throughput test system, the promising catalysts are determined among the tested catalysts, and only by analyzing them in the pressurized test system, faster and target-based progress can be achieved. And the other performance test system is the pressurized test system. In a test system, there is 1 reactor, and it requires 1 gram of catalyst. The analysis of that system is provided by conventional GC, and the analysis time of that system is 30 minutes, and here pressure can be increased up to 20 bar. Firstly, before the reaction, all catalysts were reduced under the hydrogen flow at 350 degrees Celsius, and then the reaction occurred at 310 degrees Celsius with a flow of hydrogen over carbon monoxide. This figure represents the high throughput test system results, and hydrocarbon over methane and carbon dioxide % ratio can be seen above in this figure, and the lithoolefins over the total product % ratio can be seen below, and the red color and the green color represent the highest values of that % ratios. When we look at the figure, firstly, it is divided into 2 groups with respect to their support materials, ultra-stable Y1 and the mordanite support. It is easily seen that the using of mordanite support increased the lithoolefins over total product % ratio. And here we have selected 4 catalysts, which are the 2 of them are base catalysts of 0.5 copper promoted iron catalyst, and the other 2 are holmium promoted iron copper catalyst. And these 4 catalysts were then tested at pressurized test system. In the pressurized test system, the reduction and reaction conditions were remained same, but the reaction pressure increased up to 10 bar. Here, it can be seen that the using of mordanite support increased the carbon monoxide conversion and CO2 selectivity with respect to ultra-stable Y-supported catalyst. And also the lithoolefins yield and olefin-paraffin ratio increased on the mordanite supported catalyst. Looking at the holmium promoted catalyst, the CO conversion stayed higher on the mordanite support than the ultra-stable Y1, but here the carbon dioxide selectivity decreased slightly and came closer to ultra-stable Y more supported catalyst. And also the C2-C4 lithoolefins yield and olefin-paraffin ratio was higher performance than the ultra-stable Y supported catalyst. So when we look at the overall results of pressurized test system, on the left side, I mean the base catalyst, using of mordanite support increased the carbon monoxide conversion by 27%, and C2-C4 olefin selectivity by 106%. But here, the using of mordanite support decreased the coke formation by 18%. And looking at the holmium promoted catalyst on mordanite support, it can be seen that the CO conversion increased by 28%, and C2-C4 olefin selectivity by 142%. Here, the holmium addition increased the coke formation by 12%. Although ultra-stable Y support zeolite has higher specific surface area than the mordanite support, mordanite has a higher impact on the performance results, which can be attributed to the mordanite's high acidity or low silica alumina ratio. So as conclusion, we have synthesized 24 catalysts and tested at atmospheric pressure by using high throughput test system, and the 4 catalysts were selected to be tested in pressurized test system. The addition of holmium with respect to mordanite supported base catalyst increased slightly carbon monoxide conversion and C2-C4 selectivity, increased coke formation, and decreased carbon dioxide and C5+ selectivity. And using mordanite support with respect to ultra-stable Y supported base catalyst increased carbon monoxide conversion, C2-C4 selectivity, decreased coke formation, and increased carbon dioxide selectivity and C5+ selectivity. In the feature agenda, we will, the other catalysts that show promising feature will also be tested, and the effect of different supports, different promoters, and varied reaction conditions will also be tested. And this study was supported by the Scientific and Technological Research Council of Turkey. And I would like to thank to my professors and my colleague. Thank you for listening.
Okay, thank you, Dr. Utkun Bugun, for this really good presentation. Is there any question from the participants? In fact, I had a question, but I think you explained it. I was wondering about if we create alloys, will it increase the efficiency? But I think you did it with creating iron and copper alloys, isn't it?
Yes, you are right. Actually, we are trying to add some metals. It can be alkali metals, the other transition metals to that. And after the calcination processes and drying processes, as you said, we are creating as actually alloys.
Okay, thank you.
Thank you.
And by the way, there isn't any question. Thank you again for
Thank you very much.
Good presentation. See you.
See you.
And our last presentation is from Dr. Esra Balkanlı Ünlü, and the presentation title is Effect of Molybdenum Bromated Catalytic Filter on the Partial Oxidation Reaction of Methane.
Hello.
Okay, hello.
Thank you for presenting me.
Okay, please.
First, I want to share my presentation from here. I think that's it.
Okay, good luck.
Thank you. Just wait a minute. Okay. My name is Esra Balkanlı Ünlü from Yıldız Technical University, Department of Chemical Engineering, and I will present our work. I'm sorry. There's some situation with my computer. I'm sorry again. The content will be shortly introduction to partial oxidation reaction in hydrogen energy and or experimental setups and results of the characterization and performances. Also, I will finish this presentation with the conclusion. To begin with, most of the world energy demands are fed from the fossil fuel sources, but emission of fossil fuels causes the environmental stress with its depletion as a natural fuel sources. As an economical and environmental aspect, hydrogen energy is an alternative source which plays important role in environment. Hydrogen is a clean energy source and can be replaced fossil fuels in many fields. But in nature, it exists in a chemical compound and firstly must be produced, then used in the system. As in hydrogen production, there can be categorized in 3 sections like electrochemical, thermochemical, and photochemical production methods. Hydrogen is already used in chemical and food production industry, and its production industrially from hydrocarbon sources, and most common production method is steam reforming, which provides very high energy and produce high carbon dioxide emission. To eliminate or deplete the carbon dioxide emission and simplify the process, partial oxidation reactions stand out with their syngas production and sustainable methods. A partial oxidation reaction is a one-step reaction, exothermic reaction, and produce with production of rich syngases. It have a flexible feedstock from methane-rich sources to complex hydrocarbon. Also, it's cheaper other than reformer processes. There is a non-catalytic partial oxidation reaction known as a thermal partial oxidation, which occurs at high temperatures. But high temperatures leads the complex system and consumes very high energies. Also, it's hard to maintain the main reaction. But with catalytic reaction, the ideal operation temperature can be shrink to 7,500 degrees. Their catalytic partial oxidation reaction system can be smaller construction and have a simple operation. Many catalysts have been investigated for the partial oxidation reactions, such as expensive noble metals, non-noble metals, mixed oxides, supported or unsupported catalysis. Other than the high performances of the noble metals, nickel stands out as its high efficiency. But carbon formation on nickel catalyst decreased the stability on the reaction. To support that, aluminum, lanthanum were investigated with nickel along with other metal oxides. Considering all of this, there is some criteria for the selection of catalyst. It must be higher reactivity with high mechanical thermal stability, less carbon deposition, and less expensive. In our experiments, we used nickel for their yield and mixed it with different amount of molybdenum to investigate their combination together. Molybdenum choose for their stability in the reaction. To support them, alumina used as a secondary support on calcium silicate filter, which is our main support. And calcium silicate provides us to easily handle on the reactor. In the preparation of the catalyst, different molar ratio of nickel and molybdenum solution were coated on button-shaped calcium silicate filter, which previously coated with aluminum. After drying and calcining, coating process repeated for 3 cycles. Coating process of secondary support and catalyst were performed with co-impregnation method under the vacuum. Also, our final products named as a 1.5 molar nickel molybden M1, for 1 to 1 molar nickel molybden as N2, and 1 and 1.5 molar nickel molybden as an M3. So let's continue with our reactor system. A continuous flow system that we investigated or prepared catalyst is presented in the picture of the reactor. TPR characterization and performance tests were performed in this system. There is a given TPR condition and catalytic partial oxidation reaction condition. Also, all data collected with mass spectrometer and collected data converted with given equation. In this section of presentation, I will continue with the graphical and tabular information of the results obtained by the mass spectrometer. This graphic represents our TPR results, yani reduction profile according to the temperature of the catalysis with our previous catalyst to compare with nickel filter. According to that, increasing the molybdenum ratio in the mixed oxide increased the clarity on the peaks and the final selected temperature. Reduction temperature selected respectively for M1 catalysis 60 degrees, for M2 65 degrees, also for M3 65 degrees. All catalysts treated with reduction condition before tested for the catalytic partial oxidation reaction. This graphic represents the results of the partial oxidation reaction for each catalyst. According to the graphs, optimum partial oxidation reaction, optimum temperature for the reaction of this for M1 catalysis 800 degrees, for M2 catalysis 7500 degrees, and for M3 catalysis 85 degrees. Also, we can specify that with increasing the content of molybdenum lowers the stability of the catalyst, even though M1 and M2 begins with the high initial conversion, it decreases dramatically, but it still maintains its stability, even its lower efficiency. A given table represents initial conversion of the catalysts for all temperatures, and graphic shows the comparison of all catalysts at 7500 degrees. We can classify that M2 catalyst has the best working performance at 7500 degrees. Almost 2 hours, M2 catalyst maintain at high conversion yield, which is 94%. M3 catalyst sustain this stability for up to 30 minutes at 92% methane conversion. According to the table, initial conversion of catalyst for up to 75 degrees are higher than 19%, but decreases dramatically by the time except for the M2 catalyst at 7500 degrees. To summarize this presentation, addition of molybdenum increased the optimum reduction temperature, also improved the stability by supporting the nickel at high temperatures. The optimum temperature of the catalyst for M1 is 800 degrees, for M2 7500 degrees, and for M3 8500 degrees. MT catalysis maintain its stability 7500 degrees for 2 hours at high efficiency. Also, with optimum molybdenum mixture with nickel can increase stability with a high efficiency at partial oxidation reaction. Also, we can specify that maximum yield condition for this study, 1 molar nickel molybdenum mixture and at 7500 degree. Thank you for listening. This work has been supported by the Scientific and Technological Research Council of Turkey within the 2209 program. Thank you for listening to me.
Okay. Thank you, Dr. Esra Balkanlı Ünlü, for this good presentation.
Thank you very much.
Is there any questions from the participants? Unfortunately, no, there isn't.
Thank you very much.
My area, so I don't have questions.
Okay, it's okay. Thank you very much for listening to me.
Thank you.
Have
Okay.
a nice day.
You too. Okay, dear participants, with this last presentation, we finished this session, and the next session will start at 1:30 p.m. I want to thank to all organization team for this really very, very good and beneficial Congress. I hope we can do this Congress, next Congress in live with seeing each other as in old days. Please keep yourself in health days and see you.
Thanks, dear chair and the participants. On the behalf of the organizing committee, we want to share a video from Atılım University.
Başkent Ankara'da kaliteli öğretim verilen, bilim ve teknoloji üreten, araştırma yapan, ülkenin geleceğine ışık tutan bir üniversite olmak amacıyla kurulan Atılım Üniversitesi, 24 yılı aşkın bir süredir bu hedefi gerçekleştirmek ve daha ileriye taşımak için kararlı adımlarla ilerliyor. Bu adımlardan biri olarak kurulan Atılım Üniversitesi Hidrojen Enerjisi ve Yakıt Pilleri Araştırma Grubu, enerji sistemleri mühendisliği çatısı altında çalışmalarını yürütmektedir.
Ben Profesör Doktor Yılser Devrim, Atılım Üniversitesi Enerji Sistemleri Mühendisliği bölümünde öğretim üyesi olarak görev yapmaktayım. 2014 senesinden beri lideri olduğum Atılım Üniversitesi Hidrojen Enerjisi ve Yakıt Pilleri Laboratuvarı'nda çalışmalarımızı sürdürmekteyiz. Günümüzde en fazla kullanılan yakıtlar olan hidrokarbon temelli yakıtlar, bilindiği gibi çevre kirliliğine ve karbon ayak izine sebep olmaktadır. Bu nedenle temiz ve sürdürülebilir enerji arayışı, günümüzde hali hazırdaki enerji kaynaklarının da gelecekte tükenmesi tehlikesiyle karşı karşıya olan dünya için oldukça önemli. Alternatif enerji kaynakları içinde hidrojenin sağladığı pek çok avantaj nedeniyle gelecekte önemli bir yakıt olacağı bilinmektedir. Bu nedenle hem dünyada hem de ülkemizde hidrojen enerjisi ve hidrojen enerjisine dayalı güç üretim teknikleriyle ilgili çalışmalar gün geçtikçe artmaktadır. Biz de bu kapsamda Atılım Üniversitesi Hidrojen Enerjisi ve Yakıt Pilleri Laboratuvarı olarak hidrojen üretim tekniklerinin geliştirilmesi, hidrojen üretimi için fonksiyonel nanoyapıların hazırlanması, özellikle savunma sanayi uygulaması için yakıt pili sistemlerinin geliştirilmesi ve bu sistemlerde kullanılacak olan bileşenlerin yerli olarak hazırlanması ile ilgili çalışmalarımızı sürdürmekteyiz.
Ülkemizin gelecekteki güçlü ekonomisi, yüksek yaşam kalitesi ve ulusal güvenliği için enerji alanında sürdürülecek bilimsel çalışmalar ve bu çalışmaların çıktılarının ticarileşmesi son derece önem taşımaktadır. Araştırma grubumuz geniş laboratuvar altyapısı ile hidrojen enerjisi ve yakıt pilleri alanında bilim ve teknolojinin gelişmesini sağlayarak bu teknolojilerin yerli olarak geliştirilmesine katkıda bulunmayı kendisine görev edinmiştir. Araştırma grubumuzun hidrojen enerjisi ve yakıt pilleri alanında gerçekleştirdiği çalışmalar öncelikle TÜBİTAK, Avrupa Birliği ve Üniversite Sanayi İşbirliği çerçevesinde ülkemizde önde gelen savunma sanayi firmaları ile yürütülmektedir. Hidrojen teknolojileri ve yakıt pilleri sağladıkları stratejik önem sebebiyle savunma sanayi ve uzay uygulamalarında ihracat lisansı gerektirmekte ve ticari satışları teknolojiye sahip ülkelerce engellenmektedir. Bu nedenle bu teknolojilerin ulusal olarak geliştirilmesi son derece önemlidir. Araştırma grubumuzda yürütmekte olduğumuz çalışmalar son yıllarda ivmelenerek büyümekte olan milli savunma sanayi hamlemize ve açıklanan Milli Uzay Programı'na büyük katkı sağlayacaktır. Bu kapsamda ilgili savunma sanayi firmaları ile ortak çalışmalarımız halen devam etmektedir. Araştırma grubumuzda yaptığımız çalışmalar son yıllarda özellikle hem düşük sıcaklık hem de yüksek sıcaklık proton değişim membran yakıt pili bileşenleri üzerinde yoğunlaşmıştır. Hidrojenin yakıt olarak kullanıldığı yakıt pilleri son zamanlarda yenilenebilir enerji alanında adını sıkça duyuran inovatif ve yenilikçi çözümlerin başında gelmektedir. Grubumuzda PEM yakıt pili bileşenlerinin geliştirilmesi, karakterizasyonu, yakıt pili testleri ve yakıt pili sistemlerinin hazırlanması üzerinde nitelikli araştırmalar yapılmaktadır. Yaptığımız araştırmalar neticesinde düşük maliyetli PEM yakıt pili membranları, katalizörleri ve membran elektrot ataçları ticari ürünlere eşdeğer performansla yerli ve milli olarak üretilebilmektedir. Araştırma grubumuz tarafından ülkemizde ilk defa reformat gazlar ile çalışabilen yüksek sıcaklık yakıt hücresi ve bileşenlerinin tasarımı geliştirilmesi ve mikrokojenerasyon uygulaması gerçekleştirilmiştir. TÜBİTAK tarafından desteklenen projemiz kapsamında yüksek sıcaklık PEM yakıt pili teknolojisi tüm bileşenleriyle tamamen yerli imkanlar ile geliştirilmiş ve hazırlanan prototip sistemde mikrokojenerasyon uygulaması yapılmıştır. Polibenzimidazol temelli nanokompozit membranlar yüksek sıcaklık yakıt pili sistemlerinde büyük avantaj sağlamaktadır. Çalışmalarımızda geliştirilen polibenzimidazol temelli kompozit ve çapraz bağlı membranlar ile yüksek sıcaklık PEM yakıt pili performansı arttırılmıştır. Geliştirilen sistemde hem elektrik üretilmesi hem de daha ucuz ve verimli ısınma sağlayan kojenerasyon uygulaması yapılmıştır. Gerçekleştirdiğimiz araştırmalar gerek teknolojik olarak gerekse de malzeme geliştirme konusunda ulusal bilgi birikimi sağlamamız ve gelecekte yapılacak büyük ölçekli projelere temel olması açısından önem taşımaktadır. Araştırma grubumuzun önem verdiği araştırma konularından bir tanesi, savunma sanayinde büyük öneme sahip olan yakıt pillerinde hidrojen depolama sorunu ile ilgili olarak alternatif yakıtların geliştirilmesidir. Araştırma grubumuzda hidrojen üretimi ve depolanmasına yönelik olarak sodyum borhidrür ve amonyum boran temelli hidrojen üretim tekniklerinin geliştirilmesi ve yakıt pillerine entegrasyonu ile ilgili çalışmalarımız hala devam etmektedir. Dünyada asgari ve sivil hayattaki gereklilikleri ve ticari açıdan bu pazarda bulunan büyük boşluklar sebebiyle ülkemiz için stratejik önem taşıyan bu sistemlerin geliştirilmesi ve üretilmesi ülkemiz için büyük önem taşımaktadır. Özellikle grubumuzda hazırlanan karbon nanotip ve grafen temelli akıllı ve fonksiyonel malzemeler ile hidrojen üretimi ve yakıt pili entegrasyonu alanında başarılı sonuçlar elde edilmiştir. Yenilenebilir enerji kaynakları kullanılarak yeşil hidrojen üretimi son yıllarda giderek önem kazanan bir teknolojidir. Yeşil hidrojen, sürdürülebilir, yenilenebilir elektrik çözümü sunar. Grubumuzun çalıştığı araştırma konularından biri de yenilenebilir enerji temelli yeşil hidrojen üretimi ve uygulamasıdır. Yürüttüğümüz araştırmalarda güneş enerjisi ve rüzgar enerjisi temelli hidrojen üretimi ve yakıt pili uygulamaları tasarımı ve modellemeleri yapılmaktadır. Araştırma grubumuzda yürütülen özgün araştırmalar etki değeri yüksek dergilerde makale, ödül ve patent gibi birçok nitelikli çıktılara sahiptir. Araştırma grubumuzda yürütülen çok disiplinli nitelikli araştırmalar neticesinde araştırma grubumuz ODTÜ Profesör Doktor Mustafa Parlar Eğitim ve Araştırma Vakfı'nın bilim ödülleri kapsamında hidrojen enerjisi ve yakıt pilleri alanında yaptığımız araştırmalar neticesinde 2019 yılı Teknoloji Teşvik Ödülü'ne layık görülmüştür. Ayrıca yürütülen TÜBİTAK kapsamındaki projelerimizin üstün başarıyla sonuçlanması, çok sayıda makale, bildiri ve tez öğrencisi yetiştirilmesi nedeniyle TÜBİTAK Proje Performans Ödülü'ne de layık görülmüştür. Araştırma grubu lideri Profesör Doktor Yılser Devrim, 2020 yılı dünyanın en etkili bilim insanları listesinde yer almıştır. Atılım Üniversitesi bünyesinde 2014 yılında kurulan, günümüzün en önemli ihtiyaçlarından biri olan enerji alanında nitelikli araştırmalar yapan ve araştırmacılar yetiştiren Hidrojen Enerjisi ve Yakıt Pilleri Araştırma Grubu, çalışmalarını her geçen gün artan başarılarla devam ettirmektedir.